All right, everyone, we're back. We're about ready to finish off Chapter 4. This section we're looking at is 4.4, Logarithmic Models. So this will be a little bit similar to what we did in Section 4.2, where in that section we saw just a whole bunch of examples of models involving exponential functions. Now it'll be the same sort of thing. We're going to be looking at a whole bunch of situations in which logarithmic models are used. So the really nice thing about logs is that if you look at the graph of the log, which you all know and love, it looks a little something like this. And then it goes up, and it goes up forever as you go to the right, but you notice it's going up, flattening out, and it's getting big very, very slowly. So what that means is the log function is really good for situations such as sound intensity when there's very great differences in magnitude. So for example, the loudest sound a person can hear without damaging their ears is 1,000,000,000 times, that's that many zeros, 1,000,000,000,000 times more intense than the softest sound. So a scale going from 1 to 1,000,000,000,000 is far too cumbersome to actually try to use. So if you want to talk about the intensity of a sound in terms of its intensity alone, what you would look at is something like this, watts per meter squared, where a whisper registers with that many zeros in front of it, whereas a shotgun looks like so. So what we do instead is we use a log scale, and the log scale will give us some numbers that are a little bit easier to deal with. So here's the formula. That's what it looks like. So here again, like we did in 4.2, we just sort of recognize the values, what roles they're playing. D is the decibel level, I is the intensity of the sound you care about, I sub 0 is the intensity of the softest sound a person can hear, and you just sort of plug and chug from there. So let's look at this example right here. The sound intensity of a dishwasher was measured at that many watts per meter squared. So what is the decibel level? So we can go back up, look at this formula, and again sort of just plug in the things we see in the appropriate places. So D is equal to 10 times the log. Remember, this is the common log, base 10, of the intensity of the sound, 2.5 times 10 to the negative 6, all divided by 10 to the negative 12. That's our standard sound intensity that we're using for I sub 0. So then again, right now it's just a matter of calculations. So the first thing I'm going to do is do this division right here. So I get 10 times the log of, when you perform this division, what you get is 2.5 times 10 to the 6th. And then again, you can take that log. So let me give myself a little more room here. So if you take that log, you get 6.398, and multiplying it by 10 moves the decimal point like so. So a dishwasher is about 64 decibels. Okay? So that's all well and good. When things get interesting, though, questions like this. If the intensity of one sound from one source is 10,000 times that of another, how much more is the decibel level of the louder sound than the quieter one? So one thing you might notice here is they don't give you any intensities. So that doesn't actually have to stop us. We can just make them up. So let's say that I1 is just 1. What that means then is I2, the more intense sound, is 10,000 times that, and so that's 10,000. Okay, again, the units here are watts per meter squared. So it's just a matter of calculating this. So we take 10 times, 10 times the log of 1 over 10 to the negative 12. And just to save some space, I'm going to let you in the intermediate calculations. This part would give you 12 times 10 is 120. Okay, so from there we calculate this one, and now we're going to compare to see how much higher this decibel level is. So again, use the formula. 1 over, excuse me, we don't want 1 now, do we? We want 10,000 over, that's still 10,000, sorry, over 10 to the negative 12. Here we would get, this calculation gives us 15 times 10 is 150 decibels. So we don't actually know what these sounds are or anything, but we do know that the difference in their decibel levels, if this is D1 and this is D2, D2 minus D1 is 30 decibels. So let's think about this result for just a minute. Here we've all heard, or we just saw that a dishwasher has about 64 decibels. Okay, so hopefully you all have a good idea of what a dishwasher sounds like. 30 decibels higher than that is about 95 decibels. So this isn't exact, but that's a little bit less than a rock concert. 100 decibels, I think a rock concert is around 100, between 100 and 110. So if we just sort of approximate here, a sound a little bit louder than a dishwasher is 10,000 times, let me say it this way. A rock concert, that sound intensity is 10,000 times more intense than something slightly louder than the average common dishwasher. That's sort of amazing to me, anyway. But that's, again, the beauty of the logs. We can talk about 120 decibels and 150 decibels, and that gives us a way to compare numbers that are 10,000 times apart, which is sort of nice and shocking when you really think about it. The other main type of equation that you're going to see is the earthquake intensity, the Richter scale equation. Now, if you go online looking for this, you'll actually see a couple of different ways to calculate this, but this is one of them, and this is the one we're going to be using for the sake of this section. So the earthquake intensity looks like this. The energy released by the largest earthquake ever recorded is about 100 billion, that many zeros, times more than the amount of energy of an earthquake that is barely felt. Okay, but keep in mind that's the scale we have to deal with. We have to think about earthquakes that we can barely feel and compare them to the most powerful ones we'd ever record. Okay, so we have to bridge this gap between 1 and 100 billion. And so again, taking the log is a way to do that. So again, we have these numbers. It looks fairly similar. M is the magnitude, E is the energy released, E sub 0 is a reference earthquake, which we're going to take to be 10 to the 4.4 joules. And so we can calculate things like this. I'm old enough to remember this earthquake. I was watching the World Series when it happened. The earthquake in San Francisco in 1989 released that many joules of energy. So we want to know what was its magnitude. So we plug things in their appropriate places. We say that M is equal to 2/3 times the log of the energy for the earthquake we care about. In this case, it's 5.62 times 10 to the 14th over the reference earthquake, which we know to be 10 to the 4.4 joules. And then we start cranking through this calculation. So if we perform this division, what we get is 2.237 times 10 to the 10th. We can take that log and we get, the 2/3 comes along, we get 10.350, and then finally this multiplication gives us 6.9. So this registered as a 6.9 on the Richter scale. Now I don't remember it well enough to know if that's what they called it at the time. There might have been some rounding going on here and so on, but I think that was pretty close. I think it was a 6.9 earthquake at the time. Okay, so again, the log taking these huge vast differences and making them sort of comparable really shows up when you do things like this. So I'm sure none of you are so young that you don't remember these two earthquakes. So the earthquake in Haiti in 2010 registered as a 7.0 on the Richter scale, so a little bit more damaging than the one in San Francisco. The one in Japan that caused the tsunami was a 9. Okay, but how much more powerful exactly was that? Let's find out. So we have some problems here. So we're going to call the Haiti earthquake. We're going to say that, oops, don't spell Haiti with an E. The Haiti earthquake, we're going to say that had intensity I1. So again, we're going to have to use some variables here. And the one in Japan, we're going to say is I2. So now we don't know these values, right? We're going to do some fancy stuff to solve for them in a second, but that not knowing these values doesn't prohibit us from setting up the equation. So it's 7.0 is equal to 2/3 times the log of I1, whatever it is, and that is over 10 to the 4.4 power. Okay, so again, we kind of want to try to get at this I1. So let's start breaking up this log. We saw in 4.3 that we can separate when you have a quotient on the inside. So that's 7.0 is equal to 2/3. Now, actually, before we get into that, I think I'm going to get rid of this 2/3. So let me back up a second. So to get rid of this 2/3, what I'm going to do is I'm going to multiply this whole side by 3/2. I'm going to multiply this side times 3/2. So these cancel out. 3/2 times 7 gives us 10.5. So that equals the log of I1 over 10, 4.4. So now we can break this log up. So 10.5 is equal to the log of I1 minus the log of 10 to the 4.4. But let's think about this right here. We can actually calculate that, right? We can't calculate this. We can put this into your calculator if we want, but keep in mind something. Let me come back up here a second. Just remind you that the log of x is the log base 10 of x. So what that's saying is, what power do I have to put on 10 to get this number? Coming back to our example, what power do I have to put on 10 to get 10 to the 4.4? Well, that number is just 4.4. So this is about running out of space, but 10.5 is equal to the log of I1 minus 4.4. So I can just add 4.4 to this side. So let me do that. Those go away. So let me create some room here. Sorry. So now that we have this equation, if we add 10 plus 4.4, that's 14.9. And that's equal to the log of I1. Okay, so again, think about what this is saying. What we're saying now is we're saying that log of I1 is 14.9. So what that means is 14.9 is the number we have to put on 10 to get I1. So we can deduce from that that I1 is equal to 10 to the 14.9. Okay? So that's how many joules of energy the Haiti earthquake released. Okay? So let's just keep that in the back of our minds for a second. So remember, the amount of energy released in the Japan earthquake we called I2. So, and we know that I measured as a 9.0. So we can set up a similar formula. So 9 is equal to 2/3 times the log of I2 over 10 to the 4.4, the reference earthquake. Okay? So the first thing again I'm going to do is I'm going to multiply each side by 3/2. Cancel that out. Multiply this by 3/2. Apologize for all the scrunching. But what that gives us then is 13.5, that's 9 times 3/2, is equal to the log of I2 divided by 10 to the 4.4. Okay, similar trick. We break that log up, say log I2 minus log 10 to the 4.4. The log of 10 to the 4.4 is still the number we have to put on 10, so that's still 4.4. So I'm just going to add 4.4 here to save a step. Add 4.4 to that side as well. So we have 17.9 is equal to the log of I2. So that's saying that whatever this I2 is, 17.9 is the number we have to put on 10 to get it. So therefore I2 is 10 to the 17.9. So this is all sort of well and good, but we want to know how many times more powerful the earthquake in Japan was. So we took this value, I1, and divide that into I2. So I2 divided by I1 is 10 to the 17.9 over 10 to the 14.9. But now if we think about it, we have the same base, different exponents. This is 10 to the third. But 10 to the third is 1,000. So just by going up 2 numbers on the Richter scale, what we have is an earthquake that is 1,000 times more powerful. And again, to me, that's fairly amazing. Okay? So, again, just let me recap here. What we've done so far is we've just got a little practice using a couple different kinds of models. So anytime you don't, again, just like in 4.2, you don't have to worry about memorizing these formulas or anything like that. On the homework, you can use your notes to find them. On quizzes or tests, I will give them to you to use, or maybe some other ones that involve a log, but the process is the same. Identify the particular numbers, plug them in where they go, follow order of operations, and you're good. Okay, so that concludes 4.4. That homework, you'll be able to work on that. Ask me in class when it's due. Otherwise, I hope you've enjoyed the videos. See you in class.